Hey guys, it's IBM again with another episode of Magnetic Fields and Electromagnetic Induction. Do not forget this is Physics 9702. These are paper 4 questions. These are past paper questions up to 2025 and their solutions have been given in one of the documents that you'll find on the website. The solutions have been clearly typed as you can see in this document, and you can inbox me if you want a copy with the solutions which have been clearly typed. Unfortunately, the solutions are not free. The solutions to this document, which have been clearly typed with the clear detailed explanations, you will not find them for free, but they are good and enriching, and they will help you to understand the topic fully so that you ace on your exams. Do not forget to subscribe and watch the videos on YouTube for free for you to get a clear understanding of the topic, electromagnetic fields, and magnetic flux and electromagnetic induction. Magnetic fields and electromagnetic induction. So this is part two. This is part two. And I think in part one we stopped on, I think, page 8. So let's start with page 8. So in part two, the first question is the figure shows a thin slice of semiconducting material used in a Hall probe. You must have studied the Hall probe in your class. Current I passes through the slice in the direction shown. So the direction of current has been shown. The slice is placed in a uniform magnetic field. That is means B is constant, so that two of its faces are perpendicular to the magnetic field. A steady voltage Vh is developed between face PQXW and the face SRYZ. Use the letters in the figure 6.1 to identify the faces that are perpendicular to the magnetic field. So because they say the magnetic field, a steady the slice is placed in a uniform magnetic field of flux density B, so that the two faces of its two of its faces are perpendicular to the magnetic field. A steady Hall voltage is developed between PQX, between this end here, and SRYZ and this one here. So the voltage, the PD is across PQXY and SRYZ. That means this side could be positive, the other side could be negative, or the other way around. So use the letters in the figure to identify the faces that are perpendicular to the magnetic field. So we simply use Fleming's left hand rule. Now I have tried to demonstrate with the left hand rule here. It doesn't come with the exam. I just added it here for easy explanation. So when we try to make the first finger, to point in the direction of we try to make the second finger to point in the direction of the current. So the second finger is pointing in that direction. Then uh, the thumb points in the direction of the force on the positively charged particles. If we are using Fleming's left-hand rule, with the second finger pointing in the direction of current, then the thumb points in the direction of the force acting on the positively charged particles. That means it's the positively charged particles which have been pushed to this end, which means the negatively charged particles have been pushed on the other end to create a magnetic field. To create an electric field. So using Fleming's left-hand rule, with the second finger pointing in the direction of the current that has been shown, the magnetic force on the positive charge carriers points in the direction which is PQXW. That is, it is most likely that the force on the positively charged particle will be towards that end, which is PQXW. And if that is the case, it suggests that the first finger should point downwards to show the direction of the magnetic field. If the magnetic force on the positively charged carriers was to the left, then the first finger must point upwards. In both cases, the magnetic field is perpendicular to the top and the bottom of the slices. So if If we were to reverse and say that, okay, maybe the magnetic force on the positive charge carriers is to the right hand side, still it means that the second finger, or the first finger would now point upwards and the thumb would point to the left for the current to be into the page. So still in all cases, the magnetic field is in the vertical plane, which means that the magnetic field is normal to the face PQRSP or WXYZ back to W. So in all cases, the magnetic field or the magnetic field lines are vertical or they are perpendicular to those faces. So this is going to be P, Q, R, S, and W, X, Y, Z. Okay. Explain how the steady Hall voltage VH is developed between the faces P, Q, X, W and S, R, Y, Z. How is the steady Hall voltage VH developed? Of course, as current flows through the slice, the positive charge carriers accumulate on one side and the negative charge carriers accumulate on the other side, creating what we call an electric field. A potential difference is set up, and the potential difference continues growing as more charge carriers, positive ions move to the other end, and negative ions move to the other end. So that means because an electric field has been created, an electric force or a force to the electric field also acts on charge carriers. So we now have, let's think of a positively charged particle here, which is maybe being acted on by the force due to the magnetic field towards that end to move it in that direction, making this side to be very positive. But as more positively charged particles accumulate here, it makes this one positive. It means now there will be an electric force, which is due to the electric field which has been created, and the electric force now starts repelling. It starts repelling or acting against or in the opposite direction to the magnetic field on the positively charged particle. The time comes when the force due to the electric field which has been created is equal to the force due to the magnetic field which is there. And when these two forces are equal, then the positive and negative charge carriers can no longer move to the sides. In that case, we have now a constant potential difference between PQXW and SRYZ. At that point, we say a steady Hall voltage is established. So again, Fleming's left-hand rule has come into play here. So the magnetic force on charge carriers is perpendicular to both. The magnetic force on charge carriers is perpendicular to both the magnetic field and the current. When I say force is perpendicular to field and current, that is Fleming's left-hand rule. As charge carriers are deflected to one side because of the force, as charge carriers are deflected to one side, an electric field is set up so that a Hall voltage is set up. Those are two marks. But when does this Hall voltage become steady? The Hall voltage becomes steady or constant when the electric and the magnetic force on the charge carriers are equal and opposite. So the Hall voltage becomes steady or constant when the electric and magnetic forces on the charge carriers are equal and opposite. So as the current flows perpendicular to the magnetic field, a force acts off. A magnetic force is experienced by the charge carriers. So the charge carriers are going to be deflected on one side, with the positive charge carriers on the one side and negative charge carriers on the opposite side. It sets up what we call an electric field, and because there's an electric field, a Hall voltage is set up. This Hall voltage goes on accumulating and it becomes constant when the electric force, due to the set up electric field, balances with the magnetic force. It remains now constant. The magnitude of VH is given by the equation. Sometimes this equation is not given. State the meaning of the symbols N, T, and Q. You may refer to the letters in the figure. So N, of course, for N, number of charge carriers per unit, number of free electrons per unit volume, or number density of charge carriers, I cannot refer to the diagram. So N is the number density. N is the number density of charge carriers. Or N can be the number of free electrons. You must add the word free in your explanation. Number of free electrons per unit volume. But simply the number density of charge carriers. Then T, of course, T is the thickness, which is the distance. T is the thickness, which is the distance. Now I can refer to the diagram. It can be this one, SZ. It can be RY. It can be QX. It can be PW. So T is the distance. I will say PW, or it is the distance SZ, or it is the distance QX, I think, or it is the distance RY. That is the thickness. Then Q, of course, Q is the charge on each charge carrier. Charge on each charge carrier. Okay. Suggest with a reference to the equation why the slice of the material used in a Hall voltage is thin. So we notice that VH is inversely proportional to the thickness. A thinner material means when T is smaller, it means VH is going to be larger. And therefore, a thinner material will give a large Hall voltage, which is easy to measure. So I'll say VH is inversely proportional to T, or to thickness. VH is inversely proportional to T, and so T needs to be small for VH to be large enough to measure. If T was to be big, VH would be very small, and measuring a very small quantity gives a large percentage uncertainty. So it should be too small so that VH is large enough to measure with a small percentage uncertainty. Okay. State the two conditions that must be satisfied for a copper wire placed in the magnetic field to experience a magnetic force. One, remember by Fleming's left-hand rule, the current must be perpendicular to the magnetic field for the force to exist. So there must be a current. It may not always be perpendicular, but should be having a component perpendicular to the magnetic field. For us to have a force, remember the force equals to B sine theta. So sine theta should not be 0, which means theta cannot be 0. In other words, the current cannot be parallel to the magnetic field, because B sine theta, that is the component of the magnetic field which is perpendicular to the wire or perpendicular to the current. So one, there must be a current flowing in the wire. There must be a current flowing in the wire. Number two, of course, the angle of the wire to the magnetic field must not be 0, or the wire must not be parallel to the magnetic field. So the angle of the wire to the magnetic field must not be 0, because when it is 0, it means sine 0 is 0, so the force would be 0. But if it is any value above 0, then there will be force, and the force will be maximum if the angle is 90 degrees. The direction of the long air cord solenoid is connected to a power supply so that the solenoid creates a magnetic field. The figure shows a cross section through the middle of the solenoid. Okay. The direction of the magnetic field at point W is indicated by the arrow. Three other points are labeled X, Y, and Z. On the figure, draw arrows to indicate the direction of the magnetic field at each of the points X, Y, and Z. Of course, the magnetic field is continuous. The magnetic field is continuous. So on the figure 6.1, draw arrows to indicate the direction of the magnetic field of points X, Y, and Z. So inside the solenoid, the magnetic field is uniform. At W, it is showing that the magnetic field is in this direction. So if I was to draw a continuous line, the magnetic field would be something like this. Something like that. I don't think that is good enough. Something like that. So the question is, on the figure, draw arrows to indicate the direction of the magnetic field at each of the points X, Y, and Z. So fields are represented by continuous lines as fields are supposed to be represented by continuous lines as the one I've drawn. So that means at Z, the arrow must be pointing towards the left. And of course at X, because X is inside the solenoid, so the arrow should also be in the direction here. At Y, I want people to notice that at Y, the field is going to be just a tangent pointing in this direction here. Just a tangent in that direction as we change the curve the other direction. So at point Y, it is going to be a tangent pointing in that direction. Therefore, I can now remove this. So since the field lines are continuous lines, of course at X the field is uniform and it is going to point in that direction. We have seen that at Z, because it is a continuous field line, then this is going to be pointing towards the left. And at Y, because Y is almost just outside at an angle, We say that this is going to be pointing at a tangent in this direction here. As simple as that. So at y, the field direction is a tangent to the, let me draw back the curve which I drawn with a different color. So this was something like this. Continuous line. So at y, it is just a tangent in that direction. Therefore, the arrow should be just at that angle there, that direction. As simple as that. Compare the magnitude of the flux density, that is B, at X and W. Of course, that one is the same. It is approximately the same. So flux density is approximately the same, or approximately equal. The reason as to why it is approximately equal, because inside the solenoid the field is approximately uniform. So because inside a solenoid the field is uniform. So that means the magnetic flux density is constant. Then at y and z, of course z is outside the solenoid, so the field there is going to be weaker. And y, if this was to be like a magnetic, of course this behaves as if it is a magnetic pole with the thumb pointing towards the north. This would be the north, this would be like the south. Closer to the poles, the magnetic field is greater than outside the magnetic field. So it means the flux density is greater at y than at z. So flux density is greater at y than at z. The reason? The ends of the solenoid behave like poles. I said the ends of the solenoid behaves like poles of a magnet, and the field strength is greater closer to the poles. Think of magnetic poles, where one side is north, another side is south. So a point here and a point here, it does not experience the same magnetic field as the pole. So it is stronger at this end and this end. So I'm saying the ends of the solenoid behave like poles of a magnet, and the field strength is greater closer to the poles. Since y is closer to the ends than z, then the flux density at point y is greater than that at point z. Okay. Then two parallel current carrying wires are placed near to each other in a vacuum. Explain why these wires exert a magnetic force on each other. Of course, because these wires are close to each other, it means each wire sits in the magnetic field created by the other wire. And because each wire sits in the magnetic field created by the other wire, by Fleming's left-hand rule, each wire is going to be experiencing a force if the current is perpendicular to the magnetic field at that point. Therefore, I can draw this. I just added these hands to show you for illustration. So I'll put here one wire with the current into the plane of my paper. I'll put another wire here with the current, let me put here, with the current into the plane of the paper. So one wire I'll use a different color. Let me use red. So the magnetic field around the wire, of course, we use the right-hand grip rule to tell the direction of the magnetic field. Imagine you grip the wire in your right hand. The magnetic field will be concentric circles. And I'm just taking one magnetic field line. If you grip the wire with the thumb pointing onto the paper, I wish I had added this here. If you grip the wire with the thumb pointing into the paper, because I said the magnetic field is into the paper using that X. So you grip something in your right hand with the field lines, okay, with the thumb pointing into the paper. The fingers fold in this direction here, and it means that at this wire here, which I'm going to call wire, maybe let's say this is P and this is Q. At wire Q, the magnetic field is a tangent downwards, so this is B. But remember, the current here is into the page. So if the first finger is into the page, the second finger is downwards, the thumb points to the right. So this one experiences a force caused by the magnetic field of P in that direction. So this is the force on wire Q caused by the magnetic field of wire P. Then I will do the same for the other wire using a different color. The magnetic field around the second wire is also concentric circles. I will consider one concentric circle which crosses into the position of wire P. Still, imagine you hold the wire in your right hand with the thumb pointing in the direction of the current that is into the page. The fingers point in this direction here using the right hand grip rule. That means the magnetic field at wire P, the position of wire P caused by wire Q is just a tangent upwards. So, using Fleming's left-hand rule with the current I into the page, that is the second finger pointing onto the page. If the paper is on your table, the first finger is pointing on the table. Then the thumb is pointing upwards to the direction of the magnetic field. I mean, the first finger is pointing upwards to the direction of the magnetic field. Your thumb must be pointing to the right-hand side. So the force caused on wire P because of the magnetic field of wire Q um, is to the right-hand side. So because each wire sits in the magnetic field created by the current in the other wire, by Fleming's left-hand rule, a force is created by this current, or by the currents flowing in the magnetic fields of each of the wires. Therefore, to answer this question, I will simply say that the current in a wire creates a magnetic field. The current in the wire creates a magnetic field around the wire, which are concentric circles. Each wire sits in the magnetic field created by the other wires shown above. So each wire sits in the magnetic field of the other wire as shown. Because they said you may draw a diagram, a labeled diagram. So to label this diagram, I just added B, magnetic field, and relation of the forces. Each wire sits in the magnetic field of the other wire as shown. For each wire, the current is perpendicular to the magnetic field. For each wire, the current is perpendicular or normal to the magnetic field. So the current is perpendicular to the magnetic field due to the other wire. So, according to Fleming's left-hand rule, each wire experiences a force. So each wire experiences a force according to Fleming's left hand rule. Of course, in the diagram, you don't need to include the hands. I just added them here for you to visualize how to use your left hand when trying to find the direction of the force on each of the wires, as we shall be demonstrating that later on in other questions. Okay, I want part 2 to be very, very short, and therefore I think it should stop here. Until next time, bye bye.